What's up, guys? Today I'm going to be going through the photoelectric effect. Very interesting little bit of physics that we can inspect. But in order to understand this properly, I want us to go back in time. Back in time to where physicists were debating whether or not light was a particle or a wave. So the wave nature of light had been quite well established back then. We knew that light could bounce off mirrors and reflect back, and these were all properties of waves. Newton also came around and showed us his little prism where he expanded visible light into the different colors of the spectrum. So this is quite a well-established concept back then. But then quantum physicists came around and was like, no, we want light to be particles, little packets of energy called quanta. And it was quite a big debate whether or not light was a wave or a particle. Until Einstein came around. And he said, hey, it's both. And this is where experiments such as the double slit experiment came around, where these little packets of energy, little particles of light, would bounce off, but instead of landing where they're expected to land, here and here, they form these little interference patterns that a wave would form, right? So waves would come out like so and cause an interference pattern, and that's what we see landing on the screen. And I'm not going to go into too much detail, but you can Google this. This is the double slit. But what Einstein said was, he discovered the photoelectric effect, where we have light of a certain energy, and if it meets the minimum energy for the metal, it can actually inject an electron. And in order for it to be able to do that, light itself must be a particle to interact with these electrons within the metal surface. So there is a condition, of course, that the energy of the light must meet the work function of the metal. The work function of the metal is the minimum energy required for light to eject an electron, and is given by the equation ρ equals h pho. And pho is the threshold frequency, the minimum frequency of light. H is Planck's constant. Now this is actually the exact same equation for energy of light, which is E is equal to hf. It's just labeled different so we can understand that it's for metal and not for light. But now if we take a look at this and we wanted to give a whole equation for everything together, we can get that E, the energy of light, is equal to the work function of the metal plus the kinetic energy of these ejected photoelectrons. So whatever energy comes in essentially has to come out in some form of manner. Some is absorbed by the metal and the rest is ejected in the form of kinetic energy for the ejected photoelectrons. Now what exactly is the practical uses of the photoelectric effect? Well, it can actually generate current, right? Because what is current? Current is the flow of electrons. So if we're making electrons move by shooting them out, which would cause more electrons to come in this place where those were, we're actually causing a charge to flow. So if I were to have put an ammeter here, I can get that there would be a charge registered on this ammeter. And that's where, guess what, solar panels come from. So if we take a look at how the photoelectric effect can produce current. So it's important to note the setup we have here, that the end receptor of the current is on the other side of our battery. Okay, so it's important to note that it's going through like this, which means if we increase the intensity, so which means typically if there was just a line coming out of here and there and then there's an ammeter, the only thing that would cause an increase in current would be the intensity of light. But now because we have the ejected electrons landing on the other side, an increase in the frequency of light would also increase the current, because what's happening is more light will be hitting per unit time because the kinetic energy is increasing due to the increase in frequency. Just an important distinction there. So look what happens when So we've got a sodium metal on the side of the plate. Look what happens when we start increasing the intensity of the light. We get electrons being ejected. Now, the more intense our light is, the more electrons will be ejected every second, right? So if we go full intensity, we can see that a lot more electrons are being ejected. Now we start going into the ultraviolet spectrum with a higher frequency of light. You can see the speed at which they come out is much greater. And now we can also quickly take a look at our current. I believe it's off the scales right now. There it is. So you can see as the current increases, as the intensity of light increases, so does the current. Let's scale that down a bit. And it's a pretty much a straight line proportion. But you can also see what happens if I increase the frequency due to the position of this light source. It also increases our current. And here's what the effect of different work functions will do. So if we change the metal, we can see that a lot less, actually no electrons are coming out right now because we haven't met the work function yet. If we increase our frequency, we can start getting electrons. So that's essentially the photoelectric effect in a nutshell. Thanks for watching.